Hello, and welcome to a lecture on receiver architectures. I'm Steve Ellingson. Here's an overview of this lecture. First, direct sampling. Then tuned RF. These are two examples of receiver architectures. Other examples of receiver architectures, including superheterodyne receivers. There, several variants, single, dual, and multiple conversion, and we'll talk about how these are used in FM broadcast, GSM, and land mobile radio receivers. We'll talk about the half IF problem. We'll talk about up-down superhet architecture, which is commonly used in spectrum analyzers and general coverage HF receivers. And then we'll talk about multiband, also known as divide and conquer superhet architecture. Then we'll discuss direct conversion architecture, the pros and cons, and a variant known as near zero IF architecture. Then we'll talk about superheterodyne architecture combined with direct conversion architecture, which, as I'll explain, accounts for perhaps most of the receivers that are appearing in designs today. And then a few words on frequency planning, how we select frequencies. So first, direct sampling. Direct sampling architecture is very simple. We have an antenna, we have some pre-selection or selectivity, we have an amplifier, that's the gain, that's that 50 to 110 dB that we typically require, and then the digitizer. And the rest is done in DSP. So here there's no frequency conversion. There is just filtering, that is selectivity, gain, that 50 to 110 dB that it takes to get from a typical signal level up to the level that an A to D can productively digitize, and then the digitization itself. Now note this is a simplified diagram. Usually there's several filters, one doing pre-selection, there's multiple gain stages, there's anti-alias filtering separate from the pre-selection and so on. But there is only filtering and gain and not frequency conversion. Now one variant of this is low-pass direct sampling, where we're using the first Nyquist zone. Now this is rarely used for communications applications because it requires very high second-order linearity, because there's potential for signals in the first Nyquist zone to create second-order harmonics, which appear both in the first and second Nyquist zone. A more common architecture to use these days for direct sampling is bandpass direct sampling, and that's where we use a Nyquist zone greater than 1. For example, the second Nyquist zone. This has the advantage that signals in the second Nyquist zone alias to distant Nyquist zones, so that the requirement's second-order linearity is much less. By the way, this technique is also known as undersampling. I talked about that in a previous lecture, and we'll come back to it again later. Tuned RF. This is basically the analog version of low-pass direct sampling. So here you see an analog detector instead of a digitizer. Many challenges in tuned RF architecture, so it's not very commonly used. For example, filters must have very small fractional bandwidth. That filter here must provide all the selectivity that's required at the RF frequency. The detector has to perform well at the RF frequency. See, most detectors, like AM detectors and FM detectors that are analog, work much better at lower frequencies. Furthermore, it may not be possible to implement the necessary gain, and this is because of instability due to interstage feedback. See, if I have a long string of amplifiers, we all know that it's difficult to keep the RF from feeding back through the power supply, so this is a recipe for instability. So having that 50 to 110 dB of gain or so, all at the same frequency, turns out to be a challenge, and perhaps an insurmountable challenge. There are applications for this approach, though. It does appear. It appears in applications where low cost is imperative and where you can manage to have high intrinsic immunity to interference. The two applications that come to mind right away, one is RFID tags. So in radio frequency identification, we need receivers which are extremely inexpensive. So frequency conversion is just out of the question. But we can design modulation schemes that trade off data rate for robustness to interference, and that's what allows us to do RFID tags. Another application, remote keyless entry. That is the technology that allows your key fob for your car to unlock your car from a distance. This is another application where the cost must be very low, and it's possible to come up with a scheme that has very high immunity to interference. Signal conversion superhet architecture. In this case, we have an antenna, we have pre-selection, we have gain, at least some fraction of the gain. Then we have a tuning LO doing frequency mixing, and then a lower IF stage, an IF at a lower frequency, where we have some more of the selectivity and some more of the gain. And then we can be either digitizing, that's IF sampling, or doing analog detection. Either one is common. Here it's easier to achieve the necessary gain without interstage stability problems. The reason is because RF that ends up in the power supply from this amplifier, well, it can make it back to this amplifier, but if it makes it back here, it's at a different frequency, so it's less likely to cause a problem. We also have better selectivity because the IF filter is easier to implement. The fractional bandwidth at IF is greater than the fractional bandwidth at RF, and that allows us to make a more selective filter. Furthermore, we have more options for technologies at lower frequencies. We saw that in a previous lecture. As we go down to lower and lower frequencies, there are more and more schemes, many of them having low cost, for implementing filters. Furthermore, it facilitates the use of standard IF frequencies. I'll say more about this throughout the lecture, but the idea is that the industry has gravitated towards a limited number of frequencies which are used for IF purposes, and that means that there are lots of off-the-shelf filters available for those particular frequencies. So here's an example, an FM broadcast receiver. FM broadcast exists at frequencies from 87.5 to 107.9 megahertz. Each FM signal is about 200 kilohertz wide. In this particular example, I'm going to use low side injection to get the signal to a center frequency of 10.7 megahertz. Therefore, that's the IF frequency. The bandwidth now at this IF represents a fractional bandwidth of 1.9%, which is totally manageable from a filter design perspective. The LO tuning range, since we're using low side injection, is from 76.8 to 97.2 megahertz. The image band goes from 66.1 to 86.5 megahertz. Those are determined in the usual way, that is RF minus twice the LO frequency, that is for low side injection. Now note, from here we can see why 10.7 is about the lowest IF that we can imagine using for an FM broadcast receiver, at least for a single conversion superhet. And that's because if we made the IF lower than 10.7 megahertz, this would creep up and eventually intersect the RF band, which would make it impossible to separate the image band and the RF frequencies. And we know that there's no way that we can eliminate an image after frequency conversion. So because 10.7 is the lowest frequency, which is practical for a signal conversion superhet for FM broadcast applications, and because FM broadcast is so common, 10.7 megahertz is a very common IF frequency for all applications. The half IF problem. This is characteristic of all superhet architectures. The idea is this. Let's imagine we're doing low side injection. The problem also exists for high side injection, but we'll talk about low side injection first. The RF frequency goes to the IF frequency, and the IF frequency is simply the difference of RF and LO. However, what happens if we apply a signal, or a signal exists, at a frequency of RF minus IF divided by 2? Well, in that case, we see that the output goes to IF divided by 2. Now, if there are no other impairments, that's fine. That will not cause a problem. However, if we have limited second order linearity, then we will get a second harmonic associated with that signal, and the second harmonic ends up at the IF frequency. So the half IF problem is that there are signals at this frequency which, because of the limited linearity of these stages, results in a signal overlapping the desired signal. So this is dangerous because it may be too hard to get RF minus IF divided by 2 adequately rejected by preselection. It's also dangerous because mixers and amplifiers have limited second order linearity. And Finally, it's dangerous because the subject spurious product cannot be filtered out once it's generated. In other words, once we have this, we're done. It's going to be in the output. There's no way we can discriminate between those two. This is yet another reason why we like differential implementations, especially IF and baseband. If this is differential, then, and we know that differential has intrinsically better second order linearity, then we're less vulnerable to this problem. So you see frequently that the first stages in a receiver are single-ended, and then the later stages are differential, and this is one reason why. So here's an example of the half IF problem affecting a broadcast receiver. Same receiver we talked about in the previous example, taking this tuning range, putting one of those 200 kilohertz signals at 10.7 megahertz using low side injection. Well, from the equation we just worked out, the half IF frequencies are in this range. Note here that it is impossible to filter all the frequencies vulnerable to the half IF problem by fixed preselection. Possible remedies, again, make sure you have adequate second order linearity at the IF stage, or increase the IF center frequency, because if the IF center frequency goes up, then these frequencies will go down. So this is strong incentive to use higher IF frequencies. With this in mind, we come up with a dual conversion superhet architecture. So in dual conversion, we have two frequency conversions, two IFs. The first IF we land at using a tuning LO, so this much looks very similar to a single conversion superhet, but then we do one more conversion to get to the final output frequency, and that can be done with a fixed LO. This makes it even easier to achieve the necessary gain without interstage stability problems. Why? Because now we have three stages over which to distribute the gain that we need. We've got a higher first IF, so this IF can be higher than the IF that we would need for a single conversion superhet, and that facilitates larger tuning range, and it's easier to manage the half IF problem that I just talked about. And then finally, because we have a lower final IF, we have larger fractional bandwidth for this filter, and that means better selectivity, or at least the potential for that. So here's an example of an FM broadcast receiver using dual conversion. The first IF, we could go to 10.7 megahertz. The second conversion, we could go to 455 kilohertz, which is a fairly common final IF for a dual conversion superhet. Note the first LO tunes, the second LO is fixed. Either LO may be low side or high side. However, I'll tell you, if you do both high side, you've got a huge advantage in that you get all the advantages of high side injection, which I've talked about in a previous lecture, and the spectrum comes out facing the right direction, because this gives you a spectral reversal and this gives you a spectral reversal, so the output signal is correctly oriented. And then if I really had a big issue with half IF problems, I could increase this frequency, leave this the same or increase it, and thereby adjust the requirements that I have for these preselection filters and for this filter. Now, contraindications for this approach, why we might not want to do it? Well, it's starting to get expensive now because we have more parts and we have two LOs. In fact, that second LO is going to account for a big chunk of power consumption because LOs ordinarily account for a large fraction of the power consumed by a receiver. Here's yet another example, a GSM base station receiver. GSM is a cellular protocol, becoming less common these days, but still appears in a big chunk of the world. Let's say we have this frequency range and we want to produce a signal here. Well, one way to do this is to go to an IF of 240 megahertz and then to an IF of 10.7 megahertz. That puts image frequencies in the range 389 to 414 megahertz. And this scheme is very commonly implemented. So this is a very common scheme for moving this range of frequencies to a digitizer with a center frequency of 10.7 megahertz. In fact, I can think of many base station receiver designs I've seen that use exactly this scheme. Another common version of this design uses a third conversion to go to 455 kilohertz to further improve selectivity. So very, very high performance GSM receiver might have 3 conversions, 240, then 10.7, and then 455 kilohertz, again to spread all that gain out over 4 different stages and to achieve the best possible management of all the spurious products that might result. Now, up-down architecture. In up-down architecture, the first IF is above the tuning range and the second IF is below the tuning range. This is appropriate when the tuning range must be very, very large, at least on a fractional bandwidth basis. So for example, HF general coverage receivers, this is a receiver which goes from 3 to 30 megahertz, requires up-down architecture because there's no way to tune from 3 to 30 to some IF below 3 megahertz without a conflict in preselection or image rejection. Similarly, spectrum analyzers use up-down conversion. Multiband receivers are fairly common. Let me show you an example of multiband receiver architecture that might appear in land mobile radio. In land mobile radio, there are actually several bands which are commonly used, and in some applications, such as police communications and government communications, you have to be able to operate on both bands. So let's say you have to operate on 138 to 174 megahertz and also 406 to 512 megahertz. Well, to have one receiver that does both using the same architecture can result in reduced performance. So what you can do instead is divide and conquer. So for example, 138 to 174, you could convert to 10.7 using a tuning LO covering this range. And to cover the higher frequency band, you could first go to 70 megahertz using this LO tuning range. And then by mixing with a fixed frequency of 59.3, end up at 10.7 megahertz. And then here you just select one of the two. From there, then you could go to 455 kilohertz. So that's an example of a divide and conquer architecture. Direct conversion architecture. In this case, we have an RF section and we use quadrature down conversion, as we've discussed in a previous lecture, to obtain I and Q, which is then digitized. The advantages of this technique are very large tuning range. We're not impeded by the limitations of a super heterodyne architecture. There's no image band because there's no IF. The minimum IF frequency is achieved. That is a frequency of 0. It's low cost and low power. These are all great features of the direct conversion architecture. However, there are also many disadvantages, and this tends to keep direct conversion from showing up in all but applications in which cost and power must be absolutely minimized. So here are the contraindications for direct conversion. First, the LO frequency is equal to the RF frequency. This means the LO easily leaks out the input, and the FCC, the Federal Communications Commission, and regulatory bodies throughout the world disapprove of this. Your receiver should not be transmitting. Furthermore, the LO re-enters the mixers appearing as a DC-centered tone jammer. I explained that problem when we talked about quadrature down conversion. Next, direct conversion is critically dependent on IQ balance, that is gain and phase balance, and the performance of the quadrature LO generator, which needs to produce very precisely signals which are 90 degrees out of phase. So this usually means that in situ calibration is required. You can't just assume that whatever you build is going to be sufficiently accurate. Typically, when the radio is running, there has to be something which is tweaking up the IQ balance and tweaking up the LO phase quadrature. As a result, it's very difficult to achieve large bandwidth in direct conversion architecture. Analog complex baseband processing exposes the signal to low frequency interference within the radio. There is tons of low frequency interference within a receiver. For example, modern power supplies produce tons of noise at frequencies not too far from DC. Furthermore, everything that's digital tends to produce a lot of noise. And all these signals will then overlap into the IF, which is centered at 0 hertz. This is not a problem with IF sampling architectures utilizing super heterodyne techniques. Finally, all gain must be implemented either at RF or at baseband. There is no possibility of distributing gain at other IFs, at least as I've shown it here. That means baseband gain, the gain at the IQ stage, must be implemented with extraordinarily high second-order linearity. So this is perhaps the biggest problem of all for direct conversion. Now, having said that, the popularity of direct conversion is actually increasing as the years roll on. One reason is that this issue with IQ balance is becoming increasingly easy to address using CMOS RFIC implementations. See, CMOS is the same stuff that people make computer circuits and DSP out of. So if you can put the RF on the same chip as a bunch of DSP, then the process of doing this calibration can be made a lot simpler and a lot more accurate, and also done more cheaply. Then these two problems are addressed by sound differential design. Because remember, differential design has intrinsically good common mode rejection performance, and good differential design has intrinsically good second order linearity. And these days we are getting better and better, that is, the community is getting better and better at differential design of these types of circuits. Now, a modification to the direct conversion approach is near zero IF architecture. If you look at this, it looks very similar to direct conversion. The difference is that the RF is offset from the LO by about half the bandwidth. So instead of going from RF directly to DC, instead you put the signal here, just above DC. So all the problems that we have around DC, including the LO tone jammer, are down here, whereas most of the signal's up here. So that's a near zero IF architecture. And this has a lot of advantages, especially since these days it's not much difficulty here to do that final shift of the signal to zero IF using DSP. So this is commonly used scheme in many cell phones, many base station receivers, and all kinds of receivers. However, I should point out that this also increases the minimum required bandwidth and sample rate, because here in the direct conversion architecture as classically implemented, the signal can be digitized using the lowest possible sample rate, whereas here the signal has to be sampled with a slightly higher sample rate. So FS by 2 is here, FS by 2 is here. So FS by 2 for near zero IF architecture is somewhat higher. Finally, let me show you a scheme that combines all the advantages of super heterodyne architecture and all the advantages of direct conversion architecture, and that's superhet plus quadrature conversion. And the idea is exactly what the name suggests. We have a superhet that goes to some IF, and then we do direct conversion from the IF. This combines all the advantages of superhet architecture with direct conversion architecture. Also mitigates many of the disadvantages of the two architectures. And finally, I should point out here that I'm showing superhet architecture with just one frequency conversion, but in fact there could be any number of frequency conversions there. It could be up, down, and so on. The idea here is simply to combine superhet for the first few stages with a direct conversion for the final stage. And again, this is nearly ubiquitous in some applications. For example, mobile cellular handset receivers, wireless LAN, lots of applications this architecture is used. Finally, frequency planning. Frequency planning is the process of selecting IF center frequencies and injection modes. In other words, where we're going to do low side injection versus high side injection. As we've seen, these choices have implications for pre-selection, for image rejection, and for post-mixer spurious filtering. And these frequencies and the expected levels of key spurious signals are determined using this process of frequency planning and used to set specifications for filters and linearity specifications. So here we see all these things coming together, and we see that they're related. Bandwidth, linearity, frequency plan, all these things are requirements which interact with each other and have to be traded off. Frequency planning can become very challenging for receivers operating in crowded spectrum, which these days is most of the spectrum, especially when multiple conversions are required. So frequency planning for multiple conversion superhet receivers can become very complicated. Certain standard IF frequencies are preferred so as to benefit from off-the-shelf filter designs. I've said this before, but we see once again that there's a huge advantage in terms of the process of design in having standard IFs. So the two common ones I've shown several times now are 10.7 megahertz, 455 kilohertz. Other common IFs include 45 megahertz, 70 megahertz, 140 megahertz, and there are a few other common IF frequencies which are a little bit more application specific. This concludes this lecture on receiver architectures.